Hi, in this video, we want to take a look at the log normal distribution. Okay, the log normal distribution is a highly skewed right distribution. Uh, I would say that it is the most skewed of the common typical distributions that we use. And now there are others that are more skewed, but I would say they're not common. We frequently use log normal to model things with money. All right, so anytime you're dealing with something with money, finance, something like that, be ready to use the log normal distribution. Anytime you see highly skewed right, there's a chance that log normal distribution will be a good choice. All right, for example, annual salaries within an organization frequently look like a log normal distribution. All right, so why do we call this log normal? Well, let's say that y is a normal random variable, and here I've got mean and variance of mu and sigma squared. Well, let's say that x is equal to the exponential of y. Then we say that x is a log normal random variable. So I feel like actually we should be saying x is exponential normal, but whatever. There's definitely a logarithm aspect there, log being the inverse of e. So x is log normal when x is equal to the exponential of a random variable. Okay, so now let's take a look at the density. The overall density looks very similar to regular normal, but there are two things that are different. All right, so I've got my 1, I've got my sigma, and I've got square root of 2 pi, just like regular normal, but there's a little x floating around here inside the fraction. Now, what about the exponential? Well, exponential, I see I've got squared, I've got a mu, I've got a 2 sigma squared, I've got a negative sign. All right, that's all looking the same, but I've got a log of the value. All right, so the two things are different. An x in the denominator of the fraction, and I've got a log where previously I had a regular variable. That's the difference between the formulas for normal and log normal. All right, now what's the expected value? Well, the expected value is the exponential of mu plus sigma squared over 2. Okay, now one thing to pay attention to is that mu is the expected value of the normal, not the log normal. The sigma squared is the variance of the normal, not the log normal. We have to keep that in our minds. And basically our game plan, our point of view of this is that we can go back and forth between normal and log normal freely doing u substitutions. And then our variance is going to be the exponential of the variance of the normal minus 1 times the exponential of 2 mu plus sigma squared. All right. So now let's take a look at the distribution. Let's actually derive it. So when we derive it, our game plan is I'm going to go ahead and take regular old normal random variable, and I'm going to convert it over to log normal using a substitution. Okay, so here, my first step is that I start with my regular normal density that we know and love. Now I'm going to make a substitution. I'm going to say that x is equal to e to the power of y. All right, the moment I say that, that means that y has to be equal to log of x, and the derivative of y with respect to x is 1 over x. Okay, so what I'm going to do, I'm going to come up here, and everywhere I see a y, I replace it with log of x. Okay, so then this gets replaced with log of x. Now remember that when we're talking about densities, integration is fundamental to what we're doing. So when I do a u substitution, I also have to so remember, u substitution is reversing the chain rule. Chain rule involves that derivative of the inside that comes out. That corresponds to me having to make an adjustment on that d, like what would be a dy in my integral. All right, so what I would have is a 1 over x dx over here. So the 1 over x is coming from the derivative here, and then I just tack this on. And that's how I get my u substitution aspect. And so now that shows us that we have the density. The difference between the presentation here is that it visually looks different because I used exp up above, and I put this x in the fraction here. They're mathematically equivalent, just, tinker with it a little bit. All right, so now let's think about expected values. All right, the expected value, if I'm going to do this for any old log normal, it's going to involve a completing the square step. That is kind of ugly. It's not that bad, but if you've never done this type of trick for integration, we shouldn't start with the most difficult case possible. So what I'm going to do, I'm only going to work this out for standard log normal. So I'm going to go ahead and compute the expected value, but only for when mu is equal to 0 and sigma squared is equal to 1. So I'm just taking the easiest case possible to work this out, because a lot of people have not, or really are not comfortable with this completing the square trick that I'm about to do. Okay, so let's look at the expected value. All right, so the expected value is x times the density integrated over the entire range of possible values. So remember, in the density, I've got an x in the bottom of the fraction, right? Well, when I put an x in for expected value, they're going to cancel out. So now I have this fraction times e to the negative log of x squared divided by 2. Okay, so what I'm going to do, I'm going to do a u substitution. Okay, so now here, my substitution is I'm going to say that log of x is equal to u. So this should feel very familiar to what we did just a moment ago. We're going to say that x is equal to e to the u, which tells me that dx du is equal to e to the u. Okay, so what happens? What I'm going to do, everywhere I see an x, or everywhere I see a log of x, I put in a u. That's just one spot. So here I get u squared up top. Now remember that this dx I have to convert to du. And when I do that, I need to use the derivative of x with respect to u. So this e to the u comes here, and we've made an adjustment on our differential. Okay, so now I see that I've got e to the power of something, e to the power of something. E to the power of something times e to the power of something is, well, I can do addition. So I'm going to convert it, and it's kind of hard to see. I should have adjusted this. But here I'm going to take this exponent. I'm going to take this exponent. I'm going to add them together. I'm going to put them into one exponent altogether. So I get to this. Okay, so now I'm looking at that, and can I simplify that? Can I make that a little bit easier to work with? Well, yeah. So first thing I'm going to do, I'm going to factor out that -1/2. Why? Because I don't have a love of fractions, honestly. No love. There's no love between me and fractions. So let's go ahead and just factor out that -1/2. And now when I do that, remember that I'm factoring out a -1/2 from both terms. And so this +1, after I do the factoring, is going to have a -2, because if I distribute the fraction, it needs to cancel out and give me a u. Okay, so now I've got e to the -1/2 times this parenthesis. Now I know that if I had a square here instead, then what I would have would be a normal density. So I almost have a normal density at this step. I'm missing something. All right, so if I had, let's say, u minus 1, or sorry, if I had a +1 on the inside, if I had a +1 on the inside, then I would be able to factor that, because that would be a square. And since that would be a square, I would be able to convert that to a normal random variable. Okay, so what I'm going to do, I'm going to simultaneously add 1, subtract 1. Okay, so if I add 1, I subtract 1, do I change anything? No. Now, it's very uncomfortable for a lot of people to do this because they don't think about this, but this is a tool in our tool belt that I can add and subtract the same number, and I don't change anything. Okay, so what I'm going to do, I'm going to add a 1 inside here and then subtract a 1 at the same time. Okay, so think about adding a 1 right inside here. I add a 1, I subtract a 1 simultaneously. Now, what I'm going to do is I'm going to distribute the -1/2 to the -1 that I generated, and then I'm going to break up that parenthesis. So I'm reversing, or so I'm using the distribution rule from college algebra, but I'm only using it in a very particular manner. And so when I do that, so I've got a -1 floating around. When I distribute, that becomes a +1/2. All right. So now I've got e to the -1/2 times a square. That's a square by how I built this up. And this is a constant. Okay, so now let's go ahead and factor that constant out front. And then I'm going to factor this square term. Now, when I do that, I see that I've got the constant out front. Okay. Now, when I look here, I realize that this is giving me a normal random variable with mean 1, standard deviation 1. Okay, so if I integrate any random variable over its entire range of possible values, it always integrates to 1. So therefore, this whole thing integrates to 1, and then boom, I'm just left with e to the 1/2. All right, so this gives me the expected value of standard log normal. Okay, so now let's go on to variance. The variance of the log normal is very similar. It's just that I've just got a little bit more to work with in terms of that completing the square. So I'm only going to work with standard log normal, because if you've never done this completing the square trick, I shouldn't be jumping into the hard and heavy version of it. If you want to slug it out, it will work out exactly the way it should. It's just the completing the square is kind of ugly. All right, so to get the variance, my game plan is to use this formula of the expected value of x squared minus the expected value of x squared. Okay, so what I need to do, I need to take the integral of the density times x squared. All right, well, if I've got an x in the bottom of the fraction and an x squared, one of the x's are going to cancel up top and the one on the bottom goes away. Okay, so now what I'm going to do, I'm going to do exactly the same substitution I did before. All right, well, that's going to be easy peasy lemon squeezy. So I'm going to say that u is equal to log of x is equal to the exponential u, and the derivative of x with respect to u is e to the u. Okay, so now what we're going to do is we're going to take this here. So let me back up. Everywhere I see an x, I replace it with e to the u. And on my dx term, I need to make that adjustment the same way I did before. So, dx du is equal to e to the u. So this dx gets replaced with e to the u du. We are reversing the chain rule. All right, so now I see I have e, and a bunch of exponentials. I'm going to bring that together all into one big exponential. Okay, so now I've got negative u squared divided by 2 plus 2u. Okay, so now on this step, what I'm going to do, I'm going to do exactly the same thing I did before. It's just a slightly different problem. I'm going to factor out the -1/2. All right, and that gives me with a parenthesis of u squared minus 4u. Okay, so I'm going to do the exact same trick I did. I'm going to add and subtract a term so that I can complete the square. Well, what is it going to take to complete the square on this bad boy? I'm going to do plus or minus 4. So here I add and I subtract 4. So now this part I know is a square. This part I want to get out of here. So what I'm going to do, I'm going to distribute the 1/2 to this part, into this part, and then break up that parenthesis. All right, so now that gives me all of this, and then e to the 2. Okay, well, I factor out the constant to get the e to the 2 here. Now I've got this is a square. Same trick as before. I recognize that this business over here is the density of normal distribution, mean of 2, standard deviation of 1. It's a probability distribution integrating over the entire range of possible values. Therefore, it integrates to 1. Boom, we get e squared. Now, using the variance formula, we got it. Now let's take a look at log normal distribution in R. All right, so this is very similar to what we've looked at for the other distributions in R. The main difference is that when I do my mean and standard deviations, I don't do mean and standard deviations. I do mean of log, standard deviation of log. And you'll notice that the default is 0 and 1. So what I'm doing is I put in the values for the corresponding normal random variables, the parameters of the corresponding normal random variables, and then R goes ahead and converts over for me. Okay, so let's take a look at the density function. So I'm going to use d log norm, and I've left it on default settings. Oh, something that we have the option of is working with the log of the values. So that gives us a little bit more utility of going back and forth. So let's take a look at the density, and we can see that this is pretty skewed right. Okay. Let's look at the cumulative distribution function. Got a little bit of bump, and then it goes pretty steep and then flattens out. This little bump is kind of interesting. That bump is from the skewness. Quantiles work exactly the same way as the other Q random variable, or Q distribution functions, I should say, not random variable. And then here, let's look at the random number generation. All right, so here I generated 10,000 log normal values, and you can see just how skewed this is, because if I go here, this goes all the way out to 40. You know, there are values here. There's just very, very few of them. And so there is something, you know, in the high 30s that was generated by the data. This is a highly skewed distribution. All right, well, this is all I've got for you. Take care and goodbye.